Hi class, welcome back. I'm going to study about linear approximation together with you today. So for the appetizer part, we actually have seen this question before, but I want to actually emphasize one more time if you understand why we have to use a calculus in here. So let me explain one more time when we try to find the value here. So look at my equation is y cubed minus xy equals negative 6. And if I want to find the value when x is equal to 7, try to see that can I plug in and then solve for y. If this one was a square, then we could do quadratic formula, but it's a cube. So as you see that we got stuck here, right? And luckily they actually gave me the number x and y, but normally it's not going to be easy to find. Another way that you can find that number, as you see here, we got stuck. So another way you can find this number is y is given as 2. So plug in 2 here. That is going to be 2 times 2 times 2 is 8 minus x minus times 2 is equal to negative 6. From here, try to solve. Negative 2x is equal to negative 14. So therefore, x is 7. So this time you can solve it this way. But however, did you notice that this is implicit function? Implicit function means function like a circle, which is not a function, and there's x, y, both involves with more than one term of y's. That's what implicit function is. So why we have to do this one? We cannot find y values by algebraically, although I know the x value. Then how are we going to find those values? That's why we found the tangent line around this graph. So let me show you the graph of this one. Do you guys remember? Also, I will show you briefly right now. Show the graph as you see, and then that it is going to be passing through right here 7, 2. Also, actually passing through 7, 1. As you see, this is not a function by the vertical line test. So remember the shape, and then your y-intercept is about 0, 1.9. It's not 2, I checked. So if you saw that one, and then let's briefly graph here. So it kind of looked like, I will just graph roughly. And then there was a 7, 2, and 7, 1. It passing through this way. So what I want to find this time is, I want to find value around here. And how are we gonna find the value around here? Because I know x value, but when I plug in, you see that I'm gonna get stuck with finding y values. So I'm going to use linear approximation, which is the same as a tangent line. Then I'm going to find the value of tangent line, and then I'm going to approximate the value of the black color graph. So do you see that what I try to do? So now let's look at example here and try to find our linear approximation, which is the same as a tangent line we try to find. So this case, if I want to find this red color line, first we need to find the slope by taking implicit derivative, which is y cubed minus xy equals negative 6. And if you look at, I see that there's going to be a product rule. So let's try to take a derivative. This is going to be 3y squared dy dx minus parenthesis chain rule 1 times y plus leave it and take a derivative which is 1, and then since I took the derivative with respect to y, I'm going to write dy dx equal to 0. Okay, so let's organize by dy dx. I see two terms in here. So if I factor out this one, it will be 3y squared minus x. Are you following okay? This will be minus x, and the equals minus y will go to right side. So plus y. So I got to find my derivative function, which is going to be dy dx is y over 3y squared minus x. Okay, I'm not done yet. Now we gotta plug in our point, which is 7, 2. So if I plug in carefully, 2 over 3 times 4 is 12 minus 7. So I get 2 over 5 as my slope at that moment. So I found the slope of this red color is 2 over 5, and then it's going to pass through point 7, 2. So if I want to find the tangent line, it will be y minus 2 is equal to 2 over 5 x minus 7. So I'm going to organize that it's going to be y is equal to 2 over 5 x minus 14 over 5 plus 10 over 5. So I found this line is going to be y is equal to 2 over 5x and minus 4 over 5. Yay! Does it kind of look like that to you? If you continue, do you think it's gonna go over like that? Yeah, so that's what I'm saying. So now I'm going to plug in 7 and then let's see what happened. So I'm going to plug in 7 here. Then it's going to be, I know I need more room, right? So I'm going to use here, since it's linear approximation, the equation is going to be 2 over 5x minus 4 over 5. Okay, so 7, that is going to be 14 over 5 minus 4 over 5. That gives me 2. Wow! Do you see that? Earlier, when I plug in 7, I couldn't solve by using my original function. But I can find the y value actually using linear approximation. In this case, since that is a tangent line, this coordinate is 7, 2, which I show it to you. Okay. Then, now when we have a function, what about 7.1? What about 7.1? So on the function, it's hard to see black graph 7.1. When I plug in again, y cubed minus 7.1 y is equal to negative 6. Is here anybody can solve this one for y? No, none of us. So what I am going to do, I'm going to plug into here again. So we plug in earlier 7, right? This time we are going to plug in 7.1. So 2 times 7.1 over 5 minus 4 over 5. And then let's see that what this number is. But think about this way. Well, we suppose not use calculator, honestly, because that's also the way they learn in 17th century as well. So, but however, I like to save the time with you, so you believe that I can do this by hand. Times by 2 and divide by 5 minus 4 divide by 5. I got 2.04. So I got 2.04. And then now 7.2. I want to estimate that black color. I know my graph is not really that good, but if I just make it like this, and then I'm gonna make it a little bit like that, and then now this one is 7, 7.1, 7.2. I wanna guess this coordinate 7.2. Then now same thing, I can plug in my equation as a 7.2 and do the same. I got 2.08 as estimation. So that is going to be class over or underestimation. This is going to be actually overestimation. Why? Because my tangent line, which is a linear approximation, tangent line is above my graph. So this is a overestimation, but still before we couldn't find those values in order to graph it. Now using those tangent approximation, we can find the kind of shape of the graph. So I'm going to pause and then I'm going to fill up the rest of the part and then I will come back and how I'm gonna find the actual value using the graph. Okay, so come back to me. Class, did you get to approximation number of 6.8 around the function, around the equation shown this way? So I got 1.92, 1.96, and you see there's some patterns here. So now I'm going to use a graph of the decimals and then let's try to find our actual number of the y so that how close they are. So I don't think I can get exact, but we'll see. Look at mine. So I wonder if you see my graph, kind of if I put on exactly on 7, you see that 7, 2. I don't think I can pause and come there. So now I'm going to go around 7.1. And if I go 7.1, I see as a 2.04. And then now I'm going to go 7.2. And I see about 2.08. Of course, it's a little bit, could be definitely off, but this one using 2 decimal places. And if you go 6.9, 6.8 first, I get 1.92, and then 6.9, I get 1.97, around that number. So as you saw, actually, our number was exactly the same, but I see that because they only use 2 decimal places, if they use more than 2, definitely, as we saw that, our graph is slightly above than the other, our original function, so number will be a little bit less than this one with the more decimal places. However, now I want you to see the power of calculus and what does linear approximation does, which we've been looking for tangent line last chapter, right? Now you get to see that from here when we're using it. And there is one example also in class activities. I want you to try with decimals and graph roughly, and then try to do same procedure as me and then compare, okay? So good luck. Okay, let's compare in class activities one with me. Also, very end, there's a very important explanation, so I want you to listen because that will connect it to today's main dish, the highlight part. So if you listen, it will be so much easier. So listen. Now, when I plug in, first of all, I try to plug in my number 3, and then in order to solve for y, I couldn't actually solve for y, right? Unless if they gave it to me, but without this one, we cannot. So I took the implicit derivative, and then my function is turned out to be this way. So by plugging 3, -1, luckily I found our slope turned out to be 1 at 3, -1. It doesn't look like, but actually it was 1. So if I graph this one nicely, then this was my graph at 3, -1 of my tangent line. So we are going to find the linear approximation line, which I plug in, passing through 3, -1, and then slope at that moment was 1. So if you look at, plug into the point slope form, that's how I got my linear approximation of y is equal to x minus 4. So since this one is a linear approximation, we are going to just write it legally notation of f of x, because that's not f of x. It will behave like a f of x around this number. But if you go further, definitely you're not going to use this one. If you go further, you're going to make another tangent line and you are going to find the approximation of that number. So after I found this one, I just plug in 3.1. That gives me 0.9, 3.2. So I got these linear approximation numbers nearby this function. Just think about 17th century. They couldn't find the graph of this one at all. And then actually we couldn't find this kind of function until Desmos company came out, because all the other functions should be written as y is equal to in order to graph it. But such a function like this, we cannot even solve for y is equal to. But Desmo is new company that they actually let non-function, which is implicit function, be able to graph it. Good company, right? They're from Stanford, PhD mathematicians. So keep studying, guys. Anyway, so come back here, and what I want to show you is this equation is very important today. So let's analyze. What I had was, we all know that if I write it, this is basically slope, point slope form. So I know that slope is m. Then I have a function y is equal to, let me make some room. So if I have a slope is known, then I know that my function is going to be y is equal to mx, right? And then if it passing through a comma b, then it's going to be y minus b is equal to m times x minus a, right? So if you understand this one, next one will be easier. Now I'm going to change to calculus way. So this will be rewritten as f prime as a slope, and this one we're gonna write as a comma f of a. So far so good, right? So I'm just going to plug in this one into slope, point slope form, which will be, I hope I have room to squeeze it, y minus f over a equals f prime, which is slope, times x minus a. Okay, remember this one? Then how do we solve for y? We can solve for y is equal to f prime x minus a, and then plus f over a. Yeah, it's the same thing. Yeah, it is the same thing. But in calculus, we call this one as a linear approximation. And when you look at this one, it's hard to recall. But if you analyze it as point slope form, it's exactly the same thing. So this is actually main dish explanation. So let's go back to now. Let's look at the main dish together with me. So remember this one? Okay, class, let's start the main dish. So earlier, do you remember point slope form? Y minus y1 is equal to m times x minus x1. I'm going to rewrite this one as a calculus way, as the slope is derivative f at a, and then the point passing through a comma f of a, right? This one was, the slope was m, and then point passing through x1 comma y1, so it's going to be exactly same format. So if I write it, y minus f of a equals derivative at a x minus a, Everybody following okay? So now look at this one. Point slope one, I'm just moving this one to right side. Do you see that this part is the same as this part? And then plus f of a, which is going to be, it's not y-intercept, right? It's not, because there's a transformation, and then your original function f over x. So this we call as a tangent line approximation. Remember, we call it a tangent line approximation or linearization, linear approximation. These are all the same meaning. So the expression on the right side we call as a local linearization at near x is equal to a. So local linearization, and then remember that. So where it coming from? Basically, if we have a function, and then I'm going to find the tangent line. Why we need tangent line? Because I want to approximate those numbers that sometimes the function we cannot make it, we cannot draw. So that function is going to be this one, but in this case, do you see my linearization approximation is underestimated or overestimated? This case will be underestimated, right? Underestimated. So now look at my function real value at the time has to be f of a. Then now I'm subtracting all my linear function, linear approximation function. Oh, that's going to be f of x. And then if I'm subtracting this one, which will be this function, subtracting f of a plus f derivative at ax minus a. If I subtract that whole thing, what does that mean? Do you see that I'm talking about here, the gap? This we call as an arrow bound. Do you see? One more time. This is my original function, the blue color. Subtract my linear approximation, this function, then that will give me the gap between my original function to my approximation. That we call as our arrow bound. And of course, that arrow is smaller would be better. Just think about architecture. So let's look at the example. But don't forget the name. We call this kind of a function as a local linearization, and we use it for approximation. So in old times, when they do not have a calculator, they want to actually approximate square root of 4.05. We know that square root of 4 is 2, right? But what will be square root of 4.5? About 17th century. And that time we use linear approximation, local linearization. So let's graph it first. If I graph this one, it's going to have the 3 coordinate passing through. Then I want to find the local linearization f4. So I'm going to have my tangent line f4. Okay, I should graph a little bit better. I want to have it a little bit over there. One more try. And then this is not easy. Okay, so let's say it's good enough. Then I want to find 4.05. So in order to find that, we need to find linear approximation of a red color. So find the slope. What is the slope of this one? That will be 1 over 2 square root of x. Now at where? When x is a 4. So if I plug in, that becomes 1 over 4. So I found slope at here is going to be, now I'm going to use a fancy word, f over 4 is 1/4. Slope at 4 was 1/4. And then what is the point passing through? Which is 4, 2. So let's plug in our equation. Y minus 2 equals, so exactly you can plug in here, but for me, it's the same thing. So I just plug in my point slope form. X minus 4, so I get y equals 1 over 4 minus 1 plus 2. So I get my equation as y is equal to 1 over 4 x plus 1. Okay, I hope that you got the same one. Yeah, it looks like it, right? Totally. Then I want to find 4.05. So what should I plug in this time? So if I plug in 4, do you see that if I plug in 4, I get 2? Then if it's a 4.05, oh, I should put 4.04. That would be more fun with the number, right? So 4.05, I can approximate as 4.05 divided by 4 plus 1. I will guess that number is about 2.012 something. So let me punch into calculator just to make sure. 1.4 divided by 4 minus plus 1. Okay, Yeah, I got 1.0125. So my approximation of 4.05 is a 2.0125. Then now I'm going to punch into calculator what is really 4.05 is. Sorry. And I actually got the actual number is 2.01246. I mean, there are more. But don't you think that that's actually pretty close? Not bad, right? So old times in 17th century, when they do this math by hand, that one I did it by mentally, right? So same way, and I want you to also see how they approach to find those numbers. So there will be another main in-class activities I want you to try, and I want you to see that the power of linear approximation. Okay. By the way, before we move on, I have to mention one more thing. Do you see that this one is my approximation is definitely overestimated than my actual number, right? And sorry about barking. We have a little puppy. Sorry about barking. We have a little puppy hanging out with me. So let's look at in-class activities. Did you get to see what will be the approximation number? It would be actually really cool if you get that number without using calculator, right? If it was in the classroom, I usually do. So look at when I tried to find the slope at 9, I got 1/6, and then point passing through 9,3. So I put it into my linearization format. Then I got my linearization equation as 1/6 x plus 3 over 2. Look at wiggly function is not equal, it is approximation. So I'm talking about the red color. So I want to estimate what will be square root of 9.05. So in 17th century, when they do not have a calculator, they did it exactly this way, and they divide by 6, and then I got 3.00833. Then I actually punch into the calculator square root of 9.05. Look at how close the numbers are. That is the actual number of the at the value of 9.05, and square root, that value is so close, right? So that's what is the power of calculus. Now we can communicate about it. But do you see over or under this time? It will be overestimated. If the functions look like this way and the tangent line goes that way, then it's going to be underestimated. So just careful and compare that carefully. So now let's meet me at the dessert. So welcome to dessert. We're almost done. So let's go over some of the questions. So think about sine function in old times. How do they guess this function? How do they guess this function value? So this is also one of the linearly approximation be used. So sine function, I want to find the value at 0. Then let's take a derivative, which will be cosine x, right? Don't forget. Then what's the 0 of cosine? That will be 1. So I found the slope is 1. I'm going to use now fancy notation. And then what is the equation at that time? Well, it's going to passing through 0, 0, and slope is 1. So that equation is going to y is equal to x. That's it. That's the approximation. Yeah. But do you think we can use this approximation around pi over 2? Around pi over 2. That's another thing that you guys can actually put it into decimals and then try to compare around here what's gonna look like. So let's try to look at decimals together. So I will punch in quickly for you. Let's look at decimals. First, red color is my sine function, and then my blue color is y is equal to x. When you see this one, how far do you think you can use the approximation? So do you think you can use about here? Yeah, I think it's not too bad, right? Of course, here will be even better, but what is that value? That value is, as you see, my period is going to be 2 pi, so this is a pi, that's a pi over 2, which is about 3.14 divided by 2 is 1 point, let's say just about 6. So you could even use up to your radian of 1 through 1.6. Young, I don't like that gap because this is too much. Why? If you plug in, that's going to give me 1.6, right? 1.6. But if you don't like this one, because I know that when I plug in pi over 2, which is 1, I don't like that 0.6 as an error bound. Do you see that how I found the error bound? Again, so I plug in pi over 2 to my sine function. What is a sine pi over 2? Which is 1. So I know that this value is 1, but linear approximation says at pi over 2, which is about 1.6 or 1.5 something, will give me 1.5 something. Then, do you see that my error bound is actually less than 1 or bigger than 0.5? So that's the part that you have to determine in the future at the job. How much error bound would you like to take it? So this case, if you go to, this is a 1.6, but if you go to about 1, do you think you can see the approximation of a sine function is pretty much to go along with my y is equal to x straight linear line? So I may use that around this window. And then as we mentioned, this one will be -1, so you can also use approximation around this one too, right? So that's how people guess all those values, and I want you to see from the given example. Come back to original here. So my equation that I'm going to use for approximate will be x. So I'm going to go another explanation here. So if it's equal to x, then this is actually approximation of my f of x. My f of x is my sine function, and then my approximation function is x. Then I want to find the error bound. Is this going to be over or underestimate? Do you see that it's going to be overestimate, right? So x minus f of x, this time that is going to be your error bound. And sometimes you want to make that gap is, I want to make it less than 0.1 because I want to only allow 10% error bound, something like that. But this time that x is, don't get confused, it came from you subtracting y minus f over x. Just it looks like you're subtracting x because of my function is y is equal to x. So remember, that's the error bound. That's the error. Oh, my spell's always bad. Okay. Error, right? Okay. Okay, so now let's look at one more time. So let's look at our result number 2. This time my function is a little bit harder. So what is going to be derivative? What is going to be derivative? So if I take a derivative, it's going to be, do you see this one is going to be chain rule? So e to the kx times k. So I want to find this slope at 0. That's going to e to the k times 0 times k. What would that be? Do you see that it's going to be 0 times k is 0, e to the 0 is 1, so my slope is k. So my slope is k at 0. Then what is the point passing through? If I plug in here 0, comma, e to the 0 is 1, so it's passing through 0, comma 1. So what's my equation? My approximation equation is going to be kx plus 1. That's the answer. Okay. Now there's a last one, the one more in-class activities, and then let's do it, and then let's see if you're understanding this whole section. Good luck. Okay, so how did you do? I got the derivative as a 2k e to the 2kx, and when I plug in 0, my slope is going to be 2k at 0. So mx plus b, I got 2k as my slope, and then my y-intercept as 1. So this is my linear approximation. So I hope that you guys did a good job and the understanding okay, and I will see you later.